안녕하세요.
Hello, 你好.
Hi.
Konnichiwa.
Hello. The topic we have chosen is probability, which is the branch of mathematics concerning numerical descriptions of how likely an event is to occur or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1 where, roughly speaking, 0 indicates impossibility of the event and 1 indicates certainty. There are two situations we are going to show in this video. The first one is Monty Hall problem and the second one is breast cancer possibility.
How to solve? We're going to use Bayes' theorem. Bayes' theorem is the base for something called Bayesian inference that really change how we think about probability. Now, I will introduce what is actually the theorem. Bayes' theorem is the way of finding a probability when we know certain other probabilities. The formula is probability A over B equal to probability A times probability B over A divided by the probability B. This formula tells us how often A happens given that B happens. This is for the single case where we got one B that we're interested in. We can also alternate A given B or B given A. We can change that rule around by multiplying this particular ratio, the probability of A divided by the probability of B.
Problem statement. Assume that a room is equipped with 3 doors. Behind the first and second door are black goat and grey goat, while behind the third door is an orange car. You are asked to pick a door and will win if there is a car behind it. Let's say you pick the first door. Before the door is open, the host will open one of the other 2 doors, revealing a code, and ask if you wish to change your selection to that one door left. The Monty Hall problem is deciding whether you do switch or stick to the door that you pick.
Assume there are 3 doors. C. Which door the car is behind. H. Which door Monty Hall opens. First, the player will choose a door from 3 doors. So the probability of choosing a door from 3 doors is going to be 1 over 3. Then the host knows there is a goat behind door number 2 and he opens it. There are few probabilities. First, if the player sticks to door number 1 after the host opens door number 2, the probability is going to be 1 over 2. If the player switches this door to third door after the host opens door number 2, the probability is going to be 1. Now, we're going to find the probability he sticked and switched the door. When he switched to door number 3, this will be the calculation, and the probability of choosing door is 1 over 3 as I said. If he switched the door, the probability is going to be 2 over 3. When he stick to door number 1, the probability is going to be 1 over 3.
When you pick and stick to your choice, you will have only 1 over 3 chances of winning the car. But when you pick and switch your choice, you will have 2 over 3 chances of winning the car. So the conclusion is always switch your choice.
Problem statement. According to the statistic, approximately 12% of women in worldwide have breast cancer. A woman with breast cancer has an 89% chance of a positive test from a mammogram, while a woman without breast cancer has a 32% chance of a false positive result. What is the probability a woman has breast cancer given that she just had a positive test?
Alright, so assume that a woman walks in and takes the test and she comes back with a positive test. What is the probability that this woman actually has breast cancer? In this situation, we can actually apply the Bayes' theorem. The general formula is shown at the top right corner. So how do we solve? First of all, let event A be the woman who has breast cancer and let event B equal to the result being tested positive. So we want to figure out the probability that the woman actually has cancer given that her test result was positive. So using our base theorem shown on top, we can actually come up with our solution. So if we fill in everything, it says we would have to calculate the probability that she is suffering from cancer and multiply by the probability that she tested positive given that she actually has breast cancer and divide that by the probability that she would test positive no matter it's accurate positive or false positive. Just in case you didn't understand it clearly, I would like to construct a tree diagram and hopefully it helps. In this situation, we have two possibilities. Either she has breast cancer or she doesn't have breast cancer. And in each case, we have another two situations where the result is either positive or negative. Alright, according to the situation given, we said that 12% or 0.12 probability of a woman having cancer. If the woman has cancer, we said that there is a 89% chance or 0.89 that she is tested positive and therefore there's a 11 chance or 0.11 that she is tested negative. On the other hand, if there is a 12% chance that a woman has breast cancer, therefore there will be a 88% chance that a woman don't have breast cancer. We said even you don't have breast cancer, but still there is a 32% chance of this false positive. So there's a 32% chance that she will still test positive result, and thus there's a 68% chance that she will be tested negative, which is correct. Alright, now we just want to fill in these values. So we said the probability that the woman is suffering from cancer is 12% or 0.12 and multiply by the probability that she tested positive given that she actually has breast cancer, which is 89% or 0.89, and divide by the probability that she being tested positive, which is 0.12 times 0.89 plus 0.88 times 0.32, and we'll get 0.1068 divided by 0.3884 equals to 0.275% after granting it to three significant figures. And this is the probability that she actually has breast cancer. This is how we solve real-life problems and get a better and more accurate data using Bayes' theorem.
Last but not least is the conclusion. In the first situation, which is the Monty Hall problem, we can conclude by saying that we should swap our next choice if the first pick is the goat. This is because it will double the chance of winning the cards. Hence, you only need to swap if you choose the wrong door at the start. Next, we use Bayes' theorem to know the probability of a woman has breast cancer given that she just had a positive test. Using Bayes' theorem, we can get an accurate and precise data of the patient. We can apply it in medical industry instead of getting a poor data. In conclusion, probability plays a vital role in our daily life. We can use probability to make decisions when we don't know for sure what the outcome will be. That's all. Thank you.